If you fell into a black hole right now, you wouldn't even notice it at first. The pull would be gentle, almost calm. But then, in the blink of an eye, reality would twist. For everyone watching you, time would stop. Yet for you, the fall would never end. Imagine being caught by gravity so intense that not even light can escape.
What is inside a black hole? So a black hole is made of two components.
The first brutal truth. A black hole is a region of space where gravity is so warped, so extreme, that once you cross its boundary, the event horizon, no signal, no photon, no whisper from you can escape from an outsider's view. As you approach this boundary, your image stretches, slows, reddens, and eventually seems to freeze in time. But here's the twist. You, the one falling, experience nothing dramatic at that moment. Your clock ticks normally. You cross that horizon in finite personal time. It's all about perspective. Observers on the outside never see you pass the horizon. They watch you slow down, fade away, redshift into oblivion. And what happens next? As you descend deeper, the gravitational gradient becomes savage. Your feet, if they're closer to the center, feel a pull far stronger than your head. You stretch, you compress, you elongate, you become spaghetti. Spaghettification is nature's cruel joke. Do you die instantly? Not immediately, but soon enough. Before long, you reach the singularity, a point where densities, curvature, and physics as we know them break down. Whatever remains of you is crushed, squeezed, and annihilated by the extreme fabric of space-time itself. Inside the black hole, the very roles of space and time swap. Your future becomes your fall, and escape is no longer possible. This is the paradox. From your view, you journey inward, crossing thresholds, stretching into oblivion. From everyone else's view, you fade at the edge, forever frozen in time. Now, let's go deeper. Let's explore what the mathematics, the physics, and the imagination tell us. Welcome to the abyss. When a massive star finally burns through its nuclear fuel and collapses inward, gravity wins. The star's core compresses until density soars. Billions of tons crowded into a point we call the singularity. Surrounding that is the event horizon, the boundary beyond which nothing escapes. That moment, the birth of a black hole. But black holes come in many flavors. Let's explore stellar black holes, small but fierce. These form when stars at least approximately 20 to 25 times our sun's mass collapse. After a supernova explosion, the core may compress into a stellar black hole. These weigh a few to tens of solar masses, yet pack unimaginable power. One of the smallest ever detected is J1650. Its diameter is only about as long as Manhattan. Sounds tiny, right? But its mass is 3.8 times our sun's. Imagine Manhattan, but super dense. That's intense. Intermediate and lower end supermassive. Next up, intermediate mass / lower supermassive black holes. Take the one in Messier 15. Its diameter is about twice Earth's, but it's roughly 4,000 times more massive than the Sun. Then, just below full supermassive territory, you've got black holes that are roughly half the diameter of the Sun, but massing 100,000 solar masses. It's like a miniature heavyweight in the black hole kingdom. Our galactic middleweight, Sagittarius. A star. At the center of our Milky Way sits Sagittarius, a star. Scientists estimate its mass at 4.3 million solar masses. If you drop that black hole into our solar system, its gravitational radius would stretch only to about 1/5 of Mercury's average orbit, which means shockingly small for such enormous mass. In the grand hierarchy of black holes, ours is just medium. Black holes are scattered across nearly every galaxy. Many galaxies harbor them, from dwarf galaxies up to massive elliptical giants. True heavyweights: M87, Ton 618, and Phoenix A. Now buckle up. In Galaxy M87, the central black hole weighs in at 5.4 billion suns. You could fit our entire solar system across its diameter roughly 4 times. In 2019, the Event Horizon Telescope captured its iconic shadow. But that's not the champion. Well, maybe. Meet Ton 618, a behemoth estimated at 66 billion solar masses. You could stretch nearly 40 of our solar systems across it. And then there's Phoenix A, speculated to weigh 100 billion suns. Because it's closer, we see it more recently compared to Ton 618, which might have grown more since we observed it. Of course, these are just the heaviest we currently know. The universe might still be hiding a Goliath even bigger, waiting to be found. Putting it all together: tiers, sizes, and cosmic drama. So let's line up the tiers. 1. Stellar black holes, e.g. J1650. A few solar masses, tiny diameters. 2. Intermediate, lower supermassive, e.g. M15, 100,000 mass class, bridging the gap. 3. Supermassive, e.g. Sagittarius. A-star, millions to billions of suns. 4. Ultramassive, M87, Ton 618, Phoenix A. Tens to hundreds of billions. Each class pushes physics further. The smaller ones tug on neighbors. The bigger ones reshape whole galaxies. Why these numbers matter and what scientists say. Astronomers first suspected supermassive black holes in the 1970s, observing stars whizzing near galactic centers too fast to be explained by visible matter alone. In 1974, Sagittarius A star was pinpointed as a compact radio source, hinting at something massive, hidden. Over decades, observations of X-rays, stellar orbits, and high-energy jets built a strong case. The Event Horizon Telescope later imaged M87's shadow, a visual feat that confirmed predictions from general relativity. Scientists now study how black holes grow. Do they accrete gas slowly, merge with others, or begin as massive seeds in the early universe? Some propose that primordial black holes, born in the early cosmos, not from stars, might explain parts of dark matter or hidden mass. Physicists also caution, we reach a limit when we speak of singularities. General relativity works beautifully until densities become infinite. Then quantum gravity, the unknown frontier, must take over. So, we began with a dying star collapsing into a singularity. We saw tiny but mighty stellar black holes, intermediate masses, then zoomed out to civilizations of supermassive and ultramassive giants. We've compared diameters and masses so you can feel their scale. And we've seen that in size, our Milky Way's black hole is modest. Next, we'll plunge closer. We'll feel what it's like to approach a black hole, how time becomes elastic, and how your perspective warps. Ready? Because the next chapter dives into the experience, the impossible, the poetic, the terrifying. The void waits, you press onward. Crossing the event horizon. You wouldn't feel the exact moment you slip past the event horizon. There's no flash, no alarm bell in your own frame. You cross it as if stepping off a ledge in dark vacuum. But from the outside, for distant observers, something strange happens. You appear to slow down. Your image stretches, reddens, fades, and asymptotically freezes at the edge. Time seems to stretch out, as if you never truly fall in. Meanwhile, in your frame, everything accelerates. The universe's future flashes by, stars, galaxies, time accelerating toward the inevitable. From your view, there's no pause, no hesitation. You barrel inward. This is the paradox of black holes. One story for the faller, another for the onlooker. We end where our journey into darkness begins, at the edge of mystery. Wormholes. the tantalizing bridges in theory, born from the math of Einstein and Rosen. They are solutions in general relativity that connect two distant points in spacetime, Einstein-Rosen bridges, or wormholes. Some physicists imagine, could a black hole connect to a new universe through such a tunnel? A cosmic shortcut, a secret door. But herein lies the catch. To remain stable, traversable wormholes would require exotic matter with negative energy density, something we've never observed. So wormholes remain speculative, tantalizing, mathematical whispers of what might be. But the debate continues. Fuzzballs, firewalls, holograms, each theory pushing us to rethink space, time, and what the universe allows. What draws us to these impossible questions? Why stare into the abyss? Because black holes remind us how little we truly know about existence. Every breakthrough, small, dramatic, subtle, reshapes what we accept about time, gravity, information, and ourselves. The deepest black hole in this story may well be human curiosity. Infinite, inescapable, beautiful. We fall willingly toward the unknown, hoping to learn something about the cosmos and about us. No one knows what lies inside a black hole, but we keep asking, and maybe that's the point, because the closer we get to the unknown, the more we discover about ourselves. So I ask you now, would you dare to fall? Thanks for watching. See you in the next one. And if you haven't already, be sure to subscribe. There's so much more waiting beyond the event horizon.
This is Mission Control Houston. Endeavour's roll maneuver is complete. It is now in heads down position on track for its flight to the International Space Station.